So today we will be covering the overview of the decision tree algorithm. So this series is going to be the overviews of all the basic machine learning algorithms. Please don't expect any complex mathematics to be done here. It will be the general idea of the algorithms and wouldn't be covering any much detail, but yeah, it would be good for a general point of view of algorithms. Today we are going to see the decision tree algorithm. It is a supervised algorithm. That means labeling is involved. It has a flowchart like structure, and each split is based upon some conditions and rules. It can be used for both classification as well as regression. Let me give you the basic example of the decision tree. Classification of email into spam or not spam is the classic example of the decision tree algorithm. There would be certain rules involved in it, like if there are the sample of 10 emails, then there would be a first split based upon the word free. Its example, if the word free exists, then the algorithm would be classifying it as spam. If no, then not spam. It is a general example and very basic example of the algorithm. Now let's first of all go through some basic mathematics, not at all complex, just a basic mathematics. First of all, let's understand what is entropy. You must have heard this term in chemistry. So here it is used in the same sense, a completely different meaning but the same sense. It shows randomness or uncertainty in the data set. So entropy can be understood as, if the entropy is equal to 0, then the class is called pure or zero randomness. If entropy is equal to 1, that means it's the max randomness. We try to decrease entropy in the decision tree algorithm in each step. Now let's see the general formula of the entropy. Entropy would be equal to negative summation of pi times log 2 pi. Now what is pi? Pi is that portion of the class. Pi is specific portion of the class, or it can be also understood as proportion of class I. Let me solve an example to make you clear about the entropy. Consider there are 10 samples of the emails, out of which 6 is yes, that is spam, 4 is no, that is not spam. So if I want to calculate entropy, it would be something like negative 6 by 10 log 2 of 6 by 10 plus 4 by 10 log to 4 by 10. I will directly write the values here. 0.6 times 0.737 plus 0.4 times negative of 1.322, which comes up to 0.971. So let's interpret this entropy. So if the entropy is higher, then we got impure data. If entropy is lower, then we got pure data. What do you mean by impure data? Impure data, that means there is more disorder, and pure data means there is less disorder or more order. That's the basic of entropy. Now let's move to the another mathematical term, that is information gain. Generally I will pronounce it as IG. What is IG? So consider this as an example. If this is a decision tree, so what IG does is, at each step it calculates how much entropy is reduced. So that's the basic purpose of using IG. IG measures how much entropy is reduced after each split. Let me show you the mathematical part of the IG. So information gain is equal to entropy of parent minus summation of data set of child. So this we generally refer as parent, and this is generally referred as child. In this part, if this was the part, this would be as a parent and this would be the child. This can be also called as root and nodes and etc., but that's not the concern now. So entropy would be summation of all the data set of all the childs upon data set of parent times the entropy of the child. I'll also show you what's the entropy by the example. Suppose we have 10 samples. It has two nodes, left node and right node. If left node has 4 yes and 1 no, if right node has 2 yes and 3 no, so what would be the entropy here? We calculated the entropy of the parent here. Entropy of the parent was around 0.97. Let me just check. Yeah, it was around 0.971. I'm just continuing with the same example by which I explained you the entropy here. So that's the split. We moved further and divided into the two splits. Left node had 5 samples and right node had 5 samples. Now here entropy would be my mistake. Information gain would be parent's entropy, that is 0.971 time minus entropy data set of left child upon data set of parent, that would be 5 by 10. I have calculated this entropy already to save us some time. Entropy of this was equal to 0.72 and here entropy was equal to 0.97. So now enter dataset of child upon dataset of parent times entropy of that child, which was equal to 0.72, plus dataset of left child upon dataset of parent times dataset of times entropy of the right child. Calculating this, we will get 0.971 minus 0.845. So the information gain would be equal to 0.126. Now comes the interpretation part. If information gain is higher, then we tell it was a good split. If it was lower, we got a lower value of information gain, then we tell it is not a useful split. Let me give you an example of what would a good split look like. Suppose we had 10 samples of image where we got 2 child, each containing 5 data samples. If the left child had 5 yes and 0 no's, and similarly the right child would have 0 yes and 5 no's, then it can be called as the perfect split, where we will get the highest IG. So that was an example, just to give you an idea. Now we will move to the another topic, that is Gini impurity. It is an alternative to entropy. It is an alternative to entropy, and it is used in card decision trees. Now, generally, Gini is represented as 1 minus summation of pi square. We'll go into the bit of details of what is Gini impurity. Here C represent number of classes, for example yes, no, or multiple categories. And pi represent proportion of sample class I. I will try to use annotations, keep annotations in the similar manner to avoid confusion. I'll try my best. So if we consider this example and calculate the Gini impurity, it would be 0. I'm not sure. I'll show you the calculations, but I'm just letting you know that it would be 0. Impurity, we got a perfect split, so of course the impurity is going to be the 0. That's a common sense. So we can interpret that the impurity will be 0 if it was a perfect split, and the maximum value the Gini impurity can be is equal to 0.5, which is it was equal split. It is not considered as an ideal split. Suppose let's take an example. We have 10 sample parent data set, out of which there was 10 yes and 0 no. So proportion of yes would be equal to 1. 10 by 10, which is equal to 1. Proportion of no class would be equal to 0. There is no sample, so of course it would be 0. So now, according to the formula of Gini impurity, Gini would be equal to 1 minus class proportion of summation of all the classes times its proportion square. So 1 square plus 0 square, so it is equal to 1 minus 1, so 0. Therefore a perfect split. Hope this example explains what's the perfect split. Now let me show you the example of a maximum split. If there was a data set of 10 emails and 5 emails was yes, classified as spam, 5 emails were no, that is classified as not spam. Now if we try to calculate the Gini impurity, it would be equal to 1 minus summation of all the class time proportions square, so 0.5 square plus 0.5 square. Proportion of this class would be equal to 5 by 10, 0.5. Same goes for the right class. So Gini impurity would be equal to 0.25 plus 0.25, 1 minus 0.5, which gives you 0.5. That is maximum Gini impurity. Therefore this can be interpreted as not a useful classification. In ideal cases, we should be classifying the classes. I'm just giving an example, I will remove it later. If we have 10 samples, 9 yes and 1 no, we never target for 10 yes and 0 no's. It would lead to overfitting. So yeah, that was the case. So yeah, let me show you how that would look like, so it would create the understanding. Example 3, ideal case. If there was 10 samples, we got 8 yes, 2 no's. So if I calculate the Gini impurity, it would be equal to 1 minus it would be equal to 1 minus summation of class proportion square is class proportions square, 0.8 square plus 0.2 square, which I would get 1 minus 0.64 plus 0.04, which would be equal to 0.32. So yeah, if Gini impurity is ranging from 0 to 0.5, so we can consider 0.32 as a better split. We generally target for 90% classification, perfect classification. So that's the ideal case, industry standard, we can tell. So how is Gini impurity used in decision trees? So of course, from this example you would know it helps us to decide the better splitting feature. So we analyze each and every potential split feature, find its Gini impurity to select the ideal splitting feature. That's the thing, and we try to choose the split with the lowest Gini impurity. Now once Gini impurity is done, let's move to a bit advanced topic, I am telling you guys, it's just an overview. There is too much maths and things working behind the scene, but this is just an overview video, so you would get the well-rounded brief idea of the decision tree algorithm. Without going into the much detail, you can study each and every part in much details. So yeah, now we move to overfitting and pruning. So let me write the statement. If a tree, that is a decision tree, grows too deep, it is we have too many classifications going on like that, and there would be noise in the data instead of learning pattern. There will be too much noise. So what do you mean by tree grows too deep? When the Gini impurity is above 0.4, like we are getting the higher entropy data. So if it was 10, let me take a higher 100 samples, out of which 45 lies here, 55 lies here, again 25, 20 here, it's 30, 25. If this kind of split remains, then it's creating a noise, and this is a nonsense decision tree. What would an ideal decision tree look like is it should start making decisions after few steps. Here it's okay that it divided into 2. Now we should be getting 45, and here 550. If we are getting this kind of split, that means there would be less noise and more of a learning pattern in the decision tree. I hope this example helps in what do I mean by tree grows too deep. We have to continue making the classifications, and it would be a senseless decision tree. Let me tell you an ideal depth of the decision tree is 10. There would be the ideal depth of 10 perfectly classifies training data. My mistake, so sorry. This example was meant for the noise. So if the decision tree has the depth 10, then it would be classifying the training data perfectly, but it would be failing on the new data because we are not able to segregate the data perfectly. We are just dividing the data. This is not what a decision tree is used for. So how to prevent overfitting? We can prevent overfitting by few ways. If we are programming, we will set the max depth to, let's say, 3, and that can be done. We can set minimum sample per leaf would be equal to 5. So this doesn't lead to making a leaf that is the last one as 1 1 1 1 1 1 1 1 1. Each of the leaves shouldn't have just 1 1 1 1 samples in it. And we will also make sure that there should be at least minimum 10 samples per split. So if I have 100 examples, 5 and 95, so it should not split this data. It should stop splitting that data. So to prevent overfitting. So that's basically overfitting and pruning. the decision tree. Hope it helps. So this was pruning. What we did was pruning. So then we analyzed the pre-pruning and post-pruning results. If the results are satisfactory, then we move on to the applying that decision tree algorithm. What pruning does is it tries to remove branches that do not improve accuracy. Right? I hope you are getting me. So that's the pruning part. So I hope you got an idea. Now just a small topic of performance matrices. I wouldn't go too deep in the performance metrics. I'm just giving you the overview. So in decision tree, accuracy is calculated by TP plus TN upon total samples. Right, just a second. Yeah, so for classification tree, I already told you there are two types of decision tree. One is classification and another is regression trees. For classification trees, we use accuracy as TP plus TN upon total samples. We also use some matrices as recall or F1 scores. So F1 score is important for imbalanced data. And for regression tree, we generally calculate mean square error and R square. That's basically it. So here, I hope you know that, but I'm just clarifying. TP means true positive and TN means true negative. True positive means the data was true and our algorithm also classified it as true, and true negative means the data was actually true but our algorithm classified it as false. So that's the true positive and true negative. Same goes for false positives and false negatives. You can understand the chronology behind the same. So